For coming. Can you hear me all right? Yeah?
Yeah, yeah.
Is that amplified? Yeah. Is that just my normal booming voicing here? Okay. As per the screen, this presentation does include lots of flashing images and bright lights and also the potential for things to explode, so be warned. When I was a small kid, my parents had a hi-fi that if you looked at the bars on the front, they would move in time to the music. It was crazy. It was like you could see the music. I just sat in front of this for hours and was just transfixed. By the time I was in my early teens, I had a Commodore 64 and was very into the demo scene, which is where they tried to get the Commodore to do things that they couldn't normally do. My friends, one of my best friends at the time, brought me a demo tape in '92 called Digital Acid, which was the Commodore playing samples from a well-known techno track at the time, actual musical samples, which was unheard of to me at the time. It blew my mind. But also, I absolutely loved this visual effect where the screen would flash and it would flash text up and there'd be smileys pulsing all over the place. So that kind of introduced me to the sort of both the demo scene and the rave scene in a way, because I wasn't cool enough to be in either. And I will admit that sometimes we'd turn the lights off in my bedroom and stick this on and we would wave our hands about and generally have our wee little club night. By the time I was at uni, I had a PlayStation, the original one, and it was a CD-based machine. If you put your CD into the PlayStation, a music CD, you got these awesome kind of visual effects with, like, you know, waveforms and flashing images and stuff you could control with the PlayStation controller. And even on the PlayStation, there were actual programs you could get that you could sequence your own music and include visual effects with them that would sync to the beat and produce these cool patterns on screen. So my friends and I would sit in the bar at uni and fantasize about running our own club. We call it the Big Boo after a character in Super Mario, because even though we were PlayStation fans, we were clearly Nintendo geeks at heart. And yeah, we'd sit, like, you know, we'd have the Big Boo nightclub and it would have massive screens and great graphics and all, like, you know, gaming nights and all this kind of really cool kind of nerd fantasy club stuff. The point of all this, apart from the fact that I'm a massive nerd, is that I grew up with like visual representation of music and audio. It's fascinated me throughout my life. Spoiler alert, I never did get my own club. I became a full-time professional geek instead. My job as a UI developer, working for Shopkeep, is very rewarding, and my whole career on the web has been fantastic, but it doesn't always scratch that creative itch to mix music and audio in a way that I would and visuals in a way that I would enjoy. So today, if you'll indulge me for a moment, we're going to address this imbalance. We're going to take some creative web APIs, we're going to smash them together and kind of relive that kind of 90s demo scene rave period with some attendant visuals. So apologies for the slides, they're supposed to look like this. So I'm Neil, I'm a senior JavaScript engineer at Shopkeep and the co-organizer of Belfast.js, and this is Raising the Roof with browser audio visualization. So what do I mean by that? Audio visualization is a fairly nebulous term. My definition for the purpose of this talk is not the definition that applies to all visualization, but it works for our purposes, which is that they have to be live. They accept an incoming signal from some source, be it an audio file or a microphone or, you know, some instrument, and they do a process on the audio as it's coming in. It doesn't read ahead. It's not a pre-generation thing. The visuals that come out of it should be in some way generative. They should be algorithmically based. Basically, you get an incoming audio signal, you do some computer graphic wizardry to it and spit out some visuals. And thirdly, they need to be reactive. You need to get the sense when you're watching the visuals that they're reacting to the music. So if there's a big spike in the music, or if there's a big kick drum or like a drop in the bass, you just see that reflected in the visuals. And there's tons of prior art around this, right from the 70s when Atari released the Atari Video, I want to say Scope, but I can't remember. It was one of, sorry? Video music, thank you. It was the first commercially available visualizer. It was a big hardware unit, like a VCR, and it produced very simple geometric patterns in response to music. So from there you go right through all kinds of video synth stuff, pure data, custom hardware and software, right the way through to small portable units. Even today, VR, which is starting to become an emerging area for VR. We're not looking at that stuff today. We're going to go back to the basics and try to generate some algorithmic visuals based on an incoming audio source. And so, like I say, this is not the full definition of audio visualization, but it works for my purposes. So what we're going to pick up from this today, specifically doing it in the browser, will give you a chance to, I guess, learn a few new things that you maybe wouldn't normally get into working in the web. Some creative APIs, a few kind of new structures like typed arrays and render loops, that kind of thing. You'll get a chance to learn a little bit about how we optimize performance for 60 frames a second for canvas, that kind of thing. And just generally to stretch your creative muscles a little bit more in the web space, which I think is something we all should do a bit more often. So what's the key to all this? If we want to get audio and do something with it in the browser, we need a way of grabbing it, analyzing it, and getting frequency and time data we can then use to drive our graphics. And the API to do this is a web audio API. You might not know this, but the browser contains a fully featured synth with oscillators and processing nodes for effects and delays and distortions and EQs and filters. It's all right there in Chrome, Firefox, wherever, with no extra plugins. It just sits there. And another great talk sometime would be how to create your own synth. Paddy's shaking his head there. That's classic GIF, Paddy. Come on. It's the only one of you in the. It's the only one of you in the presentation. So we have a fully featured synth in the browser with processors and with, crucially, the ability to analyze incoming audio. So that's what we're going to use in order to get this data and do something with it. So the audio API, if you can think of it like connecting guitar pedals together, it's based on the concept of nodes. You start with a source of some kind, be it a microphone or a media element or a web stream of some kind. You connect it to one or more processors, which could be everything from delays to reverbs, gain controls, filters for low pass and high pass. The one we're going to look at today is the analyzer node, which just takes the data, passes it through if you wanted to, but also provides frequency and time information on it. And then it goes to a destination normally, which is normally going to be the sound card of the device you're running the API on. For our demos today, I'm going to have an audio element, just a regular HTML5 audio element with a track on it, and is connected to an audio element source node. So when you press play on the elements, it gets picked up by the API and gets driven into the analyzer where we can grab information on it. So web audio API in 10 lines, kind of. This is enough to get you an audio context in the page, which drives all the audio API work we do. It also creates an analyzer and connects the media element to it, which then lets us start to grab data from it. So from the top, the first thing you want to do is to initialize the web audio context. It's best to only have one per page. It just lives on the window object. It used to be prefixed, but nearly all modern browsers now support this unprefixed version. And this is where your feature detection for web audio happens. It's very simple. If you don't get anything back from calling new window audio context, you can just say, sorry, we don't support web audio on whatever platform you're running. The next thing we do is we grab some elements from the DOM. It could be our media player, like we have an audio element there. We grab it and we pass it into create media element source. The audio context we created exposes all these different factory functions for things like creating different types of node. They are subclassable in most browsers. Like we could have done new media element source node, but I believe at time of writing Microsoft Edge doesn't support using those constructors, so we have to use these factory functions instead. I think when all the browsers support that, it'll be a lot cleaner code. Anyway, we create the new source node and hook it into our audio element, and then we create an analyzer node. The middle chunk is kind of where the analyzer code sits, if you like. We create an analyzer, we give it a we created a data buffer, which is like a fixed type array, which we're going to populate with when we run the analyzer. Because we're going to be operating at high frames, between 30 and 60 frames a second, and the audio data can be quite long, it's not always performant to expect to grab back a new array or a new object every time we call the analyzer routines. So we create a data buffer, which is essentially a fixed part in memory, and we say, hey, analyzer, keep populating this part of the memory whenever we want to get new data. So that's a more performant way of grabbing data than it would be if the analyzer was to try and create like a new regular array every time. And this is what's good about doing this kind of work, is you get exposed to these structures like fixed type arrays in JavaScript that we don't normally get exposed to in our day-to-day UI work, but they can be really handy if you're working with large data sets to kind of use this in a way which makes it more performance. It's more performant to iterate over a fixed type array and to perform operations on it that would be for a regular array. So the connect call is just, we've got our source node, we connected to the analyzer, which now means that the analyzer can start to get the data from that source when it plays. Those two calls at the bottom are the two main functions on the analyzer. You can get the data back by frequency, which provides volume information for the different frequencies across the frequency spectrum, or the time domain data, which is, in simple terms, the shape of the waveform at the point at which the analyzer is called. So we only get data back from the analyzer when we call these functions. So in order to continually analyze data and perform routines on it for graphics purposes, we need to call this regularly in a loop. The last note is quite a new thing because all my code pens broke the other day, and it turns out Chrome's autoplay policy has now changed to encompass the web audio API as well, which kind of makes sense. So creating this context at the top will let us do all of this, but we won't be able to play anything through the context until the user is gestured in some way. So I think that's just good practice anyway. If you have like a start button, or just listen for a click event on the window and then call context resume when it fires, and then you can continue doing what you're doing. This won't break any of your code. It just means if you try to play the audio element without otherwise touching the page first, or if you try to call the play method on the audio element through script, it'll say we can't do this because the user hasn't interacted with the page. It's probably a better thing to do on mobile, really. So from the analyzer, we get back a fixed type array with floats. You can get it back in, or sorry, with ints. You can get it back in floats too if you want to be more precise, but we're going to deal with ints. And the array on the left is what would come back from the analyzer. It's values between 0 and 255, and it's the volume for that particular frequency band. In itself, those numbers don't mean a lot to us, but if we normalize them, if we divide them by 255, we get a value between 0 and 1, which we can then use obviously as a percentage against any of the many different visual properties. You know, if you think of what we do on the web, you know, everything we express visually can be expressed as a number. Things like heights, widths, opacity, RGB values, scales, that kind of thing. So if we know how to transform those in a way that CSS or the Canvas API can understand, we can start to feed this data into visuals and see them react. Because obviously these frequency bins are going to be jumping up and down in different ways depending on what's going on in the music. So that instantly kind of makes your visuals react in a quite naive way to the frequency data coming in. This is where it gets scary. Got a live demo with audio and visuals, and it can all blow up. Now, this is in obviously the spirit of digital acid from my youth. We're going to replicate the smiley thing, and also in memory of the legend of the Big Boo, we're going to add some booze into the mix as well. These guys are just swarming across the screen. They're not, you know, they're having fun, but they're not particularly excitable at the minute. So please God, make it work. I'm not going to talk over the music because if we get a copyright strike on YouTube, I want to be able to add some like panpipes or something in here and still be able to have you hear what I'm saying. So, you get the idea. This is all CSS and the DOM. The divs or the smileys and the boos are just divs. We created about 20 of them when the page loaded. It's not very performant to keep creating new DOM elements at runtime, so there's about 20 on the page when it loads. They have either a smiley or a boo as a background image. They're absolutely positioned, and they're given the CSS animation to fly from one side of the screen to the other. When they reach the end of the screen, we listen for a JavaScript event for that animation ending. Before they go back to the start, we give them a different Y position and a slightly different scale, and then they go back to the start of their loop and go across again. The audio API, obviously, the panel on the side there shows the output from the time domain data, which is the waveform, and at the bottom of that panel, it's the frequency bin data. Bass at the left, treble at the right. It's been kind of just normalized to make it a bit more peaky, if you like. 3 bands in the middle are an averaging function we've done to separate high frequency, middle frequency, and low frequency from that data, and it's these 3 bands that these visuals are referring to, or reacting to rather. We've set a threshold internally for these 3 bands, and when the bar spikes that threshold, we do something to one of the elements, be it the background image, the text, or the smileys themselves. Just out of interest, I'm controlling this with this little MIDI controller here, which we'll get into in a minute. I just had that set up so I only got this so I could have a single pad so I could do the thing. So, how are we doing for time?
So how much of that is JavaScript and how much is CSS?
I will tell you just now, if I can get back to my slides. So, top panel CSS. Each of the divs in the DOM has a class, a smiley or a boo, same thing really. They have a keyframe animation in CSS, which is literally just to go from the left-hand side of the screen to the right. We're using VW units, which is viewport width, So those units are a percentage of the viewport width, with 100 being the full width. So it starts at -10, enough to get it off the left-hand side of the screen. It transitions via the browser, that animation, to about 110 viewport width, which puts it outside of the screen. And we kill the overflow on the DOM so it doesn't create scroll bars. So like I said, we have a reset function that we pass one of the smiley elements into, and it will give it a random duration for the next fly through. So every time the smiley goes through this loop, the speed it goes from left to right varies. Randint is just a little utility function that you use in this kind of situation. In addition, in the reset function, we give it a new Y position. So when it goes off the right-hand side in one position, when it goes back to the left and starts again, it's somewhere else on the screen. The listener there is the animation iteration. That fires every time any of the animations on that element has gone through one iteration. The infinite keyword in the CSS means this is going to run forever. So this event fires every time one loop of it ends. And that gives us a chance to get in there, make sure it's the animation we want to react to, and then do a reset on it. So the movements, the smileys going left to right, flying, changing position, that's all just CSS, no JavaScript there at all, apart from the listener to just put it back to where it was. To get the pulse of things, we use CSS variables, which are a really handy feature. You define them either on the roots of the CSS or in individual elements, and then you can use them in variable expressions for any CSS property you have there. So in this case, we're using it as a scalar for the CSS transform, which will make the smileys go like either bigger or smaller. In the JavaScript, then, we've set a threshold. It's just half. Remember, we've normalized our float data to like between 0 and 1. So when the bar gets more than halfway, we call a function that basically sets that smiley growth variable to a size that we determine based on our threshold. And that, just by setting that property, the CSS engine tells all the DOM nodes that match that smiley class to do that. And that's why we have the smileys pulsing in time to the music. The loop is just a simple request animation frame loop. Request animation frame, if you don't know, is tied to the browser's refresh rate. So it's going to hit 60 frames per second as much as possible. So we pass it a callback. It'll just keep running, and then we just we reach into our analyzer. The Viz analyzer is just it's the entity I've created to hold our audio graph and the functions that normalize the data, give us the bands, and then we just call our update Viz function and pass into it the time, and all the different frequency bands that we defined. So that kind of makes the visual function, apart from the writes to the CSS and the DOM, reasonably pure. You know, we can express a visual just by taking these parameters and then doing something to wherever we're going to be writing to. So yeah, I mentioned during that demo I was using this little pad here. This is just an I can never pronounce it, an LPD8. It's just a MIDI controller. It does no sound, nothing of its own. It's connected to my laptop via USB. And I'm using the Web MIDI API to intercept events from that and do things in the UI. In this case, I've got it hooked up to just handle this starts, so I can do the boom and get the track starting and stopping. It toggles a panel in the demos, and I've got a knob to control the volume. The volume, by the way, is just what's coming out of my speakers. The audio element is always going to go into the analyzer so we can get the data even if it's not connected to the speakers, if you know what I mean. So we request MIDI access. It returns a promise. If it passes, you then get access to a MIDI object and all the inputs connected to it. So we just attach a listener to each of the inputs, in this case 1, that whenever anything happens on this, fire a callback. If we turn any of these knobs or hit any of these buttons, it will fire an event and tell us it was either a note on or off, which is me either pressing the pad in or out, or a control code for turning a knob. And from there I can say, okay, well, I've received a twist on the last knob on this controller. I'm going to set the volume to whatever that value is. So for these kinds of live demos, it's just a nice way to control it without being able to, or without having to go in and start tweaking with the UI with the mouse. Currently, this is only officially supported in Chrome, but it's still part of the working draft. So it's nice progressive enhancement. Obviously, you're going to build your Viz and whatever tools you're using for keyboard, mouse, pointer events, whatever. But if you want to detect MIDI, there's tons of controllers out there, everything from dedicated equipment to DJ decks to rock band controllers to phone interfaces that output MIDI. If you're building a music app or a creative app that has a lot of controls, this is a really nice progressive enhancement to just offer MIDI access, and then if I'm using your graphics app, I can like program the colors of the palette or the pads or whatever you want to do. It's just a nice thing to do. So that was the DOM and CSS. Let's move into Canvas, which is where we do a lot of Viz. We're going to concentrate on 2D today. We're not going to get into WebGL. It's beyond the scope of the talk. So the canvas is the 2D pixel buffer. It's a DOM element that sits in your DOM just like a paragraph, a div, whatever, but it offers a JavaScript API and a context which lets you manipulate the pixels inside it. It doesn't have any concept at all of things like layers or objects or any kind of real state beyond like what color you last set to draw. It's very primitive with a really small API for doing things like drawing rectangles, drawing rectangles, circles, paths, a bit of image manipulation, that kind of stuff. So I know there was a talk earlier, which I didn't get to attend unfortunately, about building your own framework. The Canvas API is a perfect candidate if you want to find something and write your own sort of small framework around it. Just something to, instead of just like manually creating calls to render a circle every frame, just create like a circle object that knows how to draw itself, and a few other things that you can just use, and you'll very quickly find it becomes a really useful toolkit for graphing or for animation here, obviously, or manipulating images, pixel data, so it's worth looking at. We instantiate the canvas in a very similar way to how we instantiate the web audio API. We need a context. The context in this case, instead of coming from the window, comes from the canvas element. So we grab the canvas off the DOM, we get a context from it, in this case a 2D one. This also works with WebGL, in which case we get a different context type, but it's just going to be 2D for these demos. And then, as with the previous examples, we have a render loop. We're using a request animation frame to call this as close to the refresh rate of the browser as possible. And the context then exposes all the methods we use in the Canvas API, like clearing the screen, drawing lines, drawing rectangles, setting colors, that kind of thing. The fill style call, where we set the fill style to red, that's stateful, so the canvas will remember on the next go around what the last fill style was. You only need to change it whenever you want to actually change the color. It remembers itself between iterations, if you like. And you can see there, let's say for example that low frequency value, low freq, is a value between 0 and 1 that we got from the analyzer module. Then by drawing that bar in the top left hand corner, it's going to scale the width of the bar depending on what that frequency data is, and that's the essential way the equalizer bars in that visualization work, and how we interpret values to get the different sizes and shapes and that kind of thing going. Just a slight aside, I was introduced a while ago to a site called dwitter.com, which is a really kind of demo scene-y kind of canvas experiment site. They're basically given a tweet length field and a bunch of global variables for things like the current time, the current canvas context, a few utility functions with things like random colors and stuff like that. And they just have to, produce these awesome effects in like 128 characters. So it's code golf. I mean, you can't read that code clearly, but it's that code in isolation, just with the canvas context, is doing that above the screen. So stuff like that, where a lot of the visualization ideas can be expressed as pure functions with some injectable dependencies, I think is a really nice idea. And it's kind of the context of what we're going to do for our canvas demo. So maybe you saw these in the prior art slide. The Atari Video, what was it called again? Sorry, the Atari Video.
Oh, Atari Video Music.
Music, thank you. I don't know why I can't remember that. Atari Video Music produced very, even though it was an actual analog video synth, produced very simple geometric shapes. It was literally manipulating the RGB composite signal into a CRT TV. Another really nice box I liked was by a company called Critter and Guitari, and it was called the Rhythm Scope. It's one that this girl here is drumming. It produced, again, very simple shapes in response to audio being passed in. Obviously, I'm not going to go into it today, but AudioViz can be a massively complex, full 3D WebGL rendered, beautifully, almost photorealistic scene. But I have a real affinity for the lo-fi kind of geometric stuff. It's easier to see what's going on. So these were kind of the inspiration for what we're going to do with Canvas, which is just see how many different ways we can use very small geometric shapes in a way which is reactive to the audio and which looks visually interesting. Almost there. If I seem nervous when I do these, is because these have not been well tested, shall we say. And also because the laptops were running really hot and might blow up at any time. Okay, so there's a canvas with the NIDevConf logo on it. 5 minutes, sweet. We got the canvas elements, the NIDev logo's on top of it. We can see a bit of a weird bar there, but nothing's really happening. If you have sunglasses, use them.
Hopefully nobody gets a flashback.
You can see there the range control. It's just a HTML5 range control, and I've got it connected to the MIDI input, so it reflects the value there. It's very handy. Okay. Just by way of proving that these are actually audio reactive, not just a bunch of random flashes, if I reduce the volume of the input, you can start to see the effects start to die off to the point where they kind of become nothing, and then we bring it back up again. And then when it starts to hit those thresholds, we can start to get the flashing effects in. Okay. So what's happening there was that we're running 60 frames render loop on this. The white bar in the middle is just rendering the time data, like the waveform shape. So you've always got something appearing on the screen, even when the peaks aren't hitting. You've still got something that's visually interesting. The rest of this is just, it's an array of maybe 5 or 6 different functions that are doing, like Twitter, getting the current time, the low, mid, and high frequency peaks. And then we're literally just rendering a bunch of different squares in as many different ways as we can think of. Most of these effects were written during talks today. I was sitting in the back of the room for Alistair and Claire and blasting away at this. Clearly as a demo of how quickly we can iterate on these effects, and not because I'm just really crap at planning for these kinds of things. So yeah, there's 5 of them in an array. We've got one selected at any time for a render loop, and whenever there's a big peak, there's a chance that we can switch to a different random effect. So you get that kind of randomizer idea. Obviously I could program them into the pads and manually switch them, but with this you can kind of just sit back and it'll just work itself along. The feedback kind of effect, where it's kind of zooming in, is literally every frame we're copying the last frame of the canvas before we draw the new one, and then after we draw the new one, we paste a copy of the previous frame over the top, slightly scaled up and slightly opaque. So over time it appears to come towards us and fade out. The blur effect is incidental. It's the browser trying to scale up an image. The canvas context, in case you weren't aware, is a pixel buffer. As I said, it's not a vector format. It's an image, just same as everything else. So that's the end of that demo, and most of the explanation logic is going to be rushed through, as always. Yeah, so that was just pure functions, not pure because they're rendering out their context, basically accepting parameters, put those different effects, whatever they are, into an array, have one active at any time, and every frame we just call that function basically to draw our scene. We put them in an array. We have one selected, we have a function to pick a random one, and then during the update loop, when we get a big peak, there's a chance that it will select a different one for us. And obviously we could parameterize that so the chance gets more or less sensitive, so there's a higher chance of changes versus lower chances. You parameterize everything. You can parameterize the speed of the effects, the amount of feedback we get, everything really. So that was Canvas and DOM for web audio and web visualization. The future will be obviously all the things we can do now in graphics context with WebGL shaders, WebAssembly. If you try to run a full scene process on a canvas, you're going to get terrible performance. If you can grab that pixel data, pass it into a WebAssembly module, and get it back again, you're going to get much better frame rates. I'd like to have a WebSocket server so I could be on the dance floor, wherever that might be, with a phone and be able to manipulate the effects from my phone instead of having to have a MIDI control. That said, I'd like to parameterize a lot more of the functions so we could have better tweaks. Bring in webcam footage, game controllers, everything, and at some point I guess I should put this somewhere where people are going to maybe be paying customers and be on the dance floor where an actual DJ's playing and see if it holds up. No pressure there at all. I recommend you do this because it's a very good way to stay creative while still learning stuff in browser tech. It's a great way to kind of push the browser stuff with Canvas, web audio, everything. I think it's just a great way to do it. It's a lot of fun. And that's my last slide as always. It's always a lot of fun. I recommend that you do this. Maybe not in that particular state. But yeah, your creativity is a gift, and if you can do it in a way which means you're going to learn something about the platform you're working on at the same time, then I think it's worthwhile. So that was audio visualization in the browser. Thanks very much.